Last day we introduced De Morgan's laws, and the most important thing about these laws is the way that we can take the denial of a compound, in this case either an or an and we can turn that into something that's easy to extract information from. So if we have the denial of an or, we can turn it into a conjunction. If we have the denial of an and, we can turn it into a disjunction. And in both cases, we're left with something that's easy to work with. The laws are also valid going from right to left, but we use those a lot less often. Last day, we went through the proofs of these, and we saw how you could make use of awkward things like this, even in a proof when you don't have special rules. More on that in a moment. But the point is that for the moment, you now have these rules. When you find the denial of an or statement in a proof, it's almost always a good idea to apply De Morgan's and to turn it into a conjunction. Likewise, when you have the denial of a conjunction, an or statement, an and statement, it's almost always a good idea to just apply De Morgan's and turn it into a disjunction. Now, once we have all these rules in place, proofs will speed up. Proofs will become simpler. But it's still important for you to know how you can get by if you don't have rules like this, because it helps you understand the inner workings of proofs. So what we're going to do is we're going to continue. We're going to look at similar rules for our two remaining binary connectives. And the first one, let me just pull the page up here a bit, is this. We want to figure out what to do when you have the denial of a conditional. And what we're going to prove is that if you have the denial of a conditional, you can always turn it into the conjunction of the antecedent and the denial of the consequent. Now that makes sense because we know that conditionals are only false in one case. They're only false when they have true antecedents and a false consequent, and that's what's being said here. We can also prove this in the opposite direction from right to left, that from this conjunction we get the denial of this conditional. But right now we're not going to worry about that. We're going to work through the more useful form of this rule. And so let's think, how do we proceed here? Well, as you go through this, I strongly recommend that when I ask questions like this, you pause and you think about it. Because if you really want to master this, what you want to do is see if you can think your way through it yourself. So think about that. I want to prove the denial of this conditional leads to this conjunction. How should I begin? Well, we want to be guided by what we're trying to show. We're trying to show a conjunction. The easiest way to show a conjunction is to remember that for a conjunction to hold, both of its parts have to hold, and so we should try to show each of its parts separately. So we'll do that. We'll first try to show P, and then we'll try to show not Q. But how can we show P? Well, it's really important to remember, if you're trying to show something and nothing else is obvious, go indirect. Do an indirect proof. Some people get nervous about this. Some people think that there's something awkward and difficult about indirect proofs. This isn't so. You really want to feel free to use them because often they're the best way to get through a proof. And in this case, if we want to prove P, we will assume not P as an assumption for contradiction. Now at this point, if you remember a couple of things, the proof goes through pretty easily. The first thing to remember is this. When you have the denial of a compound in a proof and you don't have a rule that will allow you to do anything with it, or if you've been told for the sake of the exercise that you aren't allowed to use such rules, then you have to ask yourself, how is the denial of the compound going to figure in the proof? That's the situation we're in here. We don't yet have a rule for dealing with the denial of an arrow, but here we have it in the proof. It's going to have to do a job. And the answer to the question, what job does it do, is very often this. Since we're now trying to do an indirect proof, we need a contradiction. Any contradiction will do. It doesn't matter what that contradiction is. So in particular, if we could find P arrow Q itself, we would have a contradiction with line 1. So it would be to our advantage to show P arrow Q. Now, how are you going to do that? Well, you could try to do a proof, and that would actually work out quickly and easily. Or you could remember something. We have an extra rule around. We have a derived rule, and if we use it, we're going to end up where we want to go very quickly. So think about it. What's the easiest thing to do on line 3? Well, if you recall the rule arrow plus, you will know that on line 3, we can write P arrow Q. The justification is 2 arrow plus. When we have the antecedent of a conditional we want to show plus an extra tilde, we can introduce the conditional itself. As we noted before, it feels a bit like the rule of addition, and it's related to it. So now, line 1 and line 3 contradict one another. That means that we can write the contradiction sign. The justification for it is lines 1 and 3. And we've arrived at our contradiction. So, put in a scope line and draw the appropriate conclusion. The appropriate conclusion being, of course, P itself. So that comes from 2 through 4 by indirect proof. Now, what do we have to do next? Well, we have to show not Q. And you should be able to see that that's going to be very similar. So, on line 6, once again we proceed indirectly. We want to show not Q, so we assume Q. It's an assumption for contradiction once again. As soon as we get a contradiction, we're through. And given what we just said, you should be able to see very quickly what we want to put on line 7. Line 1 is going to function in this subproof in exactly the same way that it functioned in the previous subproof. It'll be 1/2 of a contradiction. The other half will be P arrow Q. Where does that come from? Once again, from the rule arrow plus. On line 7, we can write, if P then Q, the justification is 6 arrow plus. Once again, we have a contradiction. Line 7 contradicts line 1. We can write the contradiction symbol. Justification is lines 1 and 7. We already had a contradiction up here, of course, but that's now behind a scope line. That contradiction was derived relative to this assumption. We've discharged that assumption. That's why we had to do it again down here. So we've got our contradiction. We draw our scope line. And on line 9, we have not Q. Justification for that is going to be 6 through 8 indirect proof. Now our original goal was to get P and not Q. And so all we have to do is put 5 and 9 together by conjunction. And that completes our proof. So in light of this, we have a new rule. The new rule that we have, put on the next page, is not arrow. And we've derived the rule in the most basic form. I'm going to write it as a two-way rule because even though we didn't go through the derivation from right to left, it does hold, and you should do it, but you'll see that it's extremely quick and easy. The derivation from right to left is not hard if you use indirect proof. So in the basic form, the rule reads this way. From the denial of an if-then, we can go to this conjunction. From a conjunction of this form, not so usefully, but legally, we could go to the denial of this conditional. But by far, most often, you're going to want to use it from left to right. That is the basic form of the rule, but because it's often very convenient to have it, we're going to introduce a couple of obviously closely related forms, and they work this way. From the denial of a conditional, we can conclude the antecedent of the conditional. Likewise, from the denial of a conditional, we can conclude the denial of the consequent. So what we have now is a very useful derived rule, simply called not arrow. And in addition now to being able to deal efficiently with the denial of a conjunction or the denial of a disjunction, we can deal in proofs efficiently with the denials of conditionals. Now note the form here. We've been pointing out all along, form is an important and fussy matter when it comes to doing the proofs. What you have to do to you apply the rule correctly, let's take this form here, is you have to conclude the antecedent exactly. Alternatively, if we're doing it in this way, you have to conclude the consequent plus an extra tilde. And as a matter of form, that's what's required even in cases where you end up introducing some negations that you don't want. So there's one more of these to deal with, but we'll save that for the second part of this lecture. In the meantime, what you should do is make sure that you can do this proof on your own, and also go back and do as an indirect proof on your own from right to left, from P and not Q to the denial of this conditional.